So the next set, section 9.5, is going to deal with the comparison tests and the root and ratio tests. It will be the next section. There's actually two comparison tests that we'll talk about. And again, these are going to be dealing with series with non-negative terms. So all our terms have to be positive in order to apply these next series of tests. So the first comparison test we're going to talk about is the direct comparison test. So the idea behind the direct comparison test is it's to test to use the known convergence or divergence of a series to deduce the convergence or divergence of another series. So in other words, we're going to pick a series that we know what's happening, whether it's converging or diverging, and do a comparison to the series that's given to us. So here's the theorem for the conversion test. Again, we've got two series. One we will pick and one is going to be given. And again, has to be non-negative. So one series has to be less than the other series. So that's what they're saying here. The terms of this first series are less than the term of the second series. So if the bigger series converges, then the smaller series will also converge. So if the smaller series, here's the other way, that the smaller series diverges, then the bigger series will also diverge. So I always kind of do the hand slapping test. Let's see if I can do this on the video here. So here's my smaller series, my hand on the bottom. Here's my larger series with the terms on the top. So if my smaller series diverges, it's going to push that larger series out of the way. So if the smaller series diverges, so is the larger series. That's also going to diverge. On the flip side, here's my larger series, here's my smaller series. If my smaller series converges, it's going to push the smaller series to converge. However, notice if my larger series diverges, it doesn't do anything to the smaller series. So if the larger series converges, the smaller series converges. If the smaller series diverges, it'll push up. So that's the direct comparison test. That's what we mean. If the biggest series converges, the smaller series converges. So the bigger series converges, the smaller series converges. If the smaller series diverges, the bigger series also diverges. So again, if my smaller series, the hand on the bottom, diverges, so will the larger. So here are the two steps we'll use for the comparison test. We are going to guess whether a series, so we're going to look at a comparison, and we're going to see if it converges or diverges. And then we want to find a series that proves the guess to be correct. So again, the comparison test is also known as the direct comparison test. So some books will refer to it as the direct comparison test or just the comparison test. There is a hypothesis you need to remember for the direct comparison test. One, first of all our terms have to be non-negative. And again, one series has to be larger than the other series. So here's some hints to help us when we're trying to pick a series to compare it to, because that's going to be the trick. Again, these are suggestions and not intended to be formal. It's not guaranteed that they'll always work, but these are just some things when you're trying to pick a series to compare it to. Constant terms in the denominator can usually be deleted without affecting the convergence or divergence of the series. It's going to be the dominant operations. If you have a variable raised to a power, it's not going to be the constants that are going to be affecting the convergence or divergence of the series. It's the major operations. So a variable raised to a second power, a variable raised to a third power. That's what's dominating a series. If a polynomial k appears as a factor in the numerator or the denominator of u sub k, all but the leading term in the polynomial can usually be deleted without affecting the convergence or divergence of the series. If you think about how you find horizontal asymptotes, for example, if you've got x squared minus 3x plus 2 over 4x cubed minus 6x plus 1, when you're asked to find the horizontal asymptote or finding the limit as you go to infinity, notice the only thing we zero in on are the variables with the largest exponent. We delete the rest. So that's what that means. We're only looking at, when you have a polynomial, you're only looking at the leading term. This other stuff is not affecting the limit as you go to infinity. It's just the highest power in the numerator or denominator. Another note to help you when you're trying to figure out which series is larger versus smaller, the smaller the denominator, the larger the value of the fraction. So 1 over k is larger than 1 over k plus 1. For example, if you think about your fractions 1/2 and 1/3, we know that 1/2 has a smaller denominator, but we know a half is larger than a third. So again, we know that 1 over 2 is greater than 1 over 2 plus 1. So when you're trying to decide whether or not a series is larger or smaller, the constants usually in the numerator isn't going to matter. It's going to be looking at what's happening with the variable in the denominator. So again, the smaller the number on the bottom, the larger the value of the fraction. So let's talk about now using the comparison test to determine which series is going to converge or diverge. So here's a series, 1 over square root of k minus 1/2. Again, we like the suggestion, ignore the constants. The constants usually can be deleted in the denominator. So I'm going to do a direct comparison to the series k is equal to 1 to infinity of 1 over what's remaining is that square root of k or k to the 1/2. So now you should recognize this. This is your p series. And again, notice your exponent is between 0 and 1. So 1 over k to the 1/2, we know by your p series is going to diverge. So now, in order to use your direct comparison for this, we got to make sure it meets the hypothesis. First of all terms are positive. And again, we know they are because if you plug in 1 for k, we know that the terms will be positive. And now, next we have to decide, is one series larger than another? So let's take a look at 1 over k to the 1/2 and do a comparison with 1 over k to the 1/2 minus 1/2. The series is given. So again, we know that 1 over k to the 1/2 is going to have the larger denominator. So we know that this is your smaller series because we're always going to be subtracting 1/2. So this number we know is going to be smaller than this number. So this is my smaller series. So think about 1 over 2 minus 1 over 2 minus 1/2. Again, this denominator is going to have a smaller number, but we know this series will be larger. So we know that 1 over k to the 1/2 is going to be smaller than 1 over k to the 1/2 minus 1/2. So since my smaller series is diverging, so remember my hands, smaller series diverging, what's going to happen with the larger series? That's also going to diverge. So since the smaller series diverges, I know this series will diverge by your direct comparison test. So here's another example. K is equal to 1 to infinity of 1 over 2k squared plus k. Again, constants can be deleted. And again, we're only going to concentrate on that highest power for k. So I'm going to do a direct comparison to the series k is equal to 1 to infinity of 1 over k squared. And again, this is another p series. And because 2 is greater than 1, by your p series, I know this is going to converge. So now again, I have to make sure that the conditions are met for the direct comparison test. First of all terms are positive, which they are because I plug in a 1 for k. I know right away that the denominator is always going to be positive. Now I need to check that one series is larger or smaller than another. So I need to take 1 over k squared and do a comparison to 1 over 2k squared plus k. So again, 1 over k squared, again, I know that this denominator will be a larger number. The 2k squared plus k will produce a larger number than the 1 over k squared. So this is my larger series. So I know that 1 over k squared is greater than 1 over 2k squared plus k. So since my larger, which is what I know is happening, converges, then I know the series is going to converge by your direct comparison test. So that's how the direct comparison test works. Another comparison test is called the limit comparison test. The underlying idea of this test is to use the known same idea as our direct comparison. We want to know what's happening with a particular series to deduce the convergence or divergence of another series. So again, we've got two series. Again, this focusing. Let me try and adjust this focusing a little bit. There we go. So again, we're going to have a series given to us, and we have to pick a series. And again, all of our terms have to be positive terms. So the way the limit comparison test works is we're going to find the limit, and we're going to make a ratio. The numerator is the series we don't know what's happening. That's the given. And we're going to divide it by a series that we're comparing it to, the series we know what's happening. So the way the limit comparison series works, so when we calculate this limit, as long as it's finite, meaning we can find it, and the limit is greater than 0, then both series are going to behave the same way. Both will converge or both will diverge. So again, the strategy to look at is to look at the dominant terms in the series to try and find something to compare it to. The dominant terms would be the largest exponent. If you've got an exponential function, logs or trig functions, and find a simple, similar series to make the comparison. The limit comparison test works well with messy algebraic series compared with a p-series. Find the dominant term in the numerator and denominator, set up the ratio and reduce, and use this as a guess. To use the limit comparison test, you must first know at the convergence or divergence of the series, and then find a series that supports it. So use your limit comparison test to determine whether the following series converges or diverges. So again, notice in the numerator it is a constant. The denominator, you've got a constant of 4, constant of 1. Remember, we can eliminate those constants of 4 and 1. So I'm going to do a comparison, a limit comparison of 3 over k to the 1/2. And again, I'm going to compare this to my, actually I can just do a comparison of 1 over k to the 1/2. Again, I know that this is a p-series. And again, I know that 1/2 is between 0 and 1. So by my p-series, I know that 1 over k to the 1/2 is going to diverge. So the way my limit comparison test works is I'm going to find the limit as k goes to infinity. I'm going to make a ratio. Take the series that's given. I'm going to divide it by the series I'm comparing it to, the 1 over k to the 1/2. Again, when I divide, I'm going to multiply by the reciprocal. So that'd be k times k to the 1/2 over 1. So the limit as k goes to infinity of 3k to the 1/2 over 4k to the 1/2 plus 1. So notice what's happening. The degree of the numerator is the same as the degree of the denominator. So the limit's going to be 3/4. So since 3/4 is greater than 0, then by my limit comparison test, I know that both these series are going to have to behave the same way. So this original series is going to diverge. So next I've got the 6 over 2 to the k minus 3. So again, when I take a look at 6 over 2 to the k minus 3, I can do a comparison to 1 over 2 to the k. So I'm going to compare it to my series k is equal to 1 to infinity. So 1 over 2 to the k, again, I'm looking at that particular series. Excuse me, I got something in my throat right now. Let me do a pause. Hold on one moment. Let me pause this so I can go clear my throat. Okay, I fixed that. So now let's go back and take a look at B. So I'm going to do a comparison to 1 over 2 to the k. So again, looking at 1 over 2 to the k, again, if you look at this particular series, remember we can write this in the form as 1/2 all raised to the k power. So 1 over 2 to the k is a geometric series, and because the absolute value of 1/2 is less than 1, then by your geometric series, this is going to converge. So now let's take a look and let's use the limit comparison test for part B. So I'm going to find the limit as k goes to infinity. Again, I'm going to take the series that I know, so I'm going to take that 6 over 2 to the k minus 3, and I'm going to divide it by the series I'm comparing to. Again, when I divide, I'm going to multiply by the reciprocal, so I'm going to multiply that by 2 to the k over 1. So when I find the limit as k goes to infinity, that's going to give me 6 times 2 to the k over 2 to the k minus 3. So notice the degree of the numerator will be the same as the degree of the denominator. So this limit's going to be a 6. So again, I know that 6 is greater than 0, so both these series are going to converge. So now if you take a look at the next one, k is equal to 3 to infinity, the cube root of k plus 2 divided by k minus 2. So again, I can write this as k plus 2 to the 1/3 over k minus 2. Now notice this is a case where the powers of the numerator and denominator are different. So to find a good p-series to compare this to, what you want to do is you want to find the difference between the powers. To find the p-series to compare it to. So you have 1/3 minus 1. So I'm going to do a comparison to a series k is equal to 3 to infinity of 1 over k. And again, the difference between 1/3 and 1 is 2/3. So when you look at a, which appears that you're going to do a comparison to a p-series, and you notice the degrees are not the same, to find a p-series to do a comparison to, take the difference between the two powers. So again, I know that this is a p-series, and 2/3 I know is between 0 and 1. So by my p-series, this is going to diverge. So then I'm going to do my limit comparison test, the limit as k goes to infinity, take the series that's given, the k plus 2 to the 1/3 over k minus 2. I'm going to divide it by the series I'm comparing it to, which means I'm going to multiply by the reciprocal. Now remember, since I'm doing the limit as k goes to infinity, I'm really concerning about the largest degree of what's happening in the numerator. So if I was to multiply all this out, I know that the highest degree of this numerator, k to the 2/3 times a k to the 1/3, would give me a k in the numerator. Over the largest of the denominator is going to be a k minus 2, which is going to be equal to 1. So since 1 is greater than 0, I know both these series are going to behave the same. So they're both going to diverge. Again, so you don't need to multiply all this out. Again, the idea is if you were to multiply it out, I know that I'd want to find the largest degree of the numerator and denominator.